Okay, good morning everyone. My name's Chris Ogden. I'm a forensic seismologist at AWE Blacknest, which is the UK's NDC. And today I'd like to talk to you a little bit about some of the work we've been doing on using full moment tensor solutions to look at the differences between earthquakes and announced nuclear tests in the DPRK. So I thought I'd start with a little bit of the motivation why we're doing this. So at AWE Blacknest, we need to accurately characterize seismic sources of interest. And there's a number of kind of methods, if you like, at our disposal. They include source depth, MBMS ratios, looking at the amplitude ratios of PNS, and then also looking at more complex waveform analysis methods. And they can be quite time-consuming in the last case. So moment tensor solutions have long been proposed as sort of a method to characterize these sources. If you think out there in the literature, there's plenty of examples of this over the last 20, 30, 40 years. And so the aims of this sort of talk, of this project, is really to look at using different types of these sources that are out there in the literature, different methods, and then try and understand the differences between the isotropic component, which if you like, is the kind of volume expansion or contraction, and then these kind of more the complex and hard to explain components, if you like, which is the compensated linear vector dipole, CLVD, and then the double couple, which we're familiar with. So in terms of characterizing events, MBMS is often used as sort of one of the standards, and that screens out 40% of the events in the REB as being earthquakes. But that leaves 60% of events that aren't and need to be sort of looked at and investigated. And so that's, that poses a problem in terms of time and availability. In addition, these sources aren't always easy to characterize, even when you have time on your side and plenty of analysis techniques. So there's plenty of examples in the literature of events being characterized as earthquakes when there were explosions, as explosions when there were earthquakes. A good example is the Pakistan nuclear test from 1998, where one of the studies identified P waves from a local event to that network as being the S wave from the explosion. And so when you look when you plot up its ratios, it plots within the earthquake population rather than the explosion population. And that's denoted by the red circle. In addition, you have examples of explosions producing reverse polarity surface waves, and then that obviously poses a problem if you're going to invert for these using a surface wave inversion scheme. And then the final point is more just for interest, really, that shallow dip-slip thrust events can often produce explosion-like waveforms and MBMS ratios. So you have these waveforms that, if you have the wrong distribution of stations, can look very much like an explosion when they're just an earthquake. So I thought I'd just quickly move on to what our data set is about. So we're looking at DPRK, and there's 6 explosions and a collapse event immediately after the last explosion. And then there are 5 earthquakes from the LEB. Some of those are located very near to the test site, and 2 of them are more further away in southern China. I'll be using Green's functions from the Herman wave number integration method and using just a simple 1D velocity model from Sean Ford. In terms of stations, we're using regional stations, and at the frequencies that I'll use, it's primarily surface waves. These include the IDC stations, KSRS, USRK, and KLR. But it also includes all the Earthscope stations that are available. And you can see on the plot on the right that some stations record 1 of the events, and whereas a lot of the stations record 12 of these events. The method of choice for this beginning is the MT time method. And that's a well-documented, well-written code that's publicly available. And it's It's quite easy to get working and intuitive in how it works. Importantly, it has these time shifts, and these are effectively corrections that you make to the waveform, pushing them forward or backward in time in order to correct for errors effectively in your velocity model in the region. And so these time shifts are of the order of a few seconds, but if your velocity model is particularly inaccurate, it might move up 5, 6, 7 seconds. I thought I'd just show you some of an example of our explosions. So this is from DPR-Ch2, which was the best constrained waveform. And we're getting these variance reduction, which is VR, that's kind of how well your Green's functions, which are your synthetic data, fits your observed seismograms. And what you can see is that they do fit very well, waveform for waveform on the right-hand side in 3 components. What's interesting is that, I guess what you'd expect from an explosion is that the vertical and radial, which are the Rayleigh waves, are larger amplitude than on the tangential, which is the Love waves primarily, which makes sense for an explosion source. And generally, for all of these explosions, the isotropic component dominates in a positive sense. So that's why you're seeing the kind of grey shaded circle in the isotropic component and overall moment tensor. For the collapse event that was immediately after DPR-Ch6, I'll focus a little bit on this for a couple of minutes. When you produce and spend as much time as possible, you work out all the time shifts accurately, you find that actually it does have a negative isotropic component. That makes sense because we're expecting it to be a collapse. And it's got quite a large CLVD component, and that combined leads towards a horizontal closing crack, which you might expect if you had a cavity that's then collapsed. What's interesting is that the time shifts are all required to make this moment tensor are 4 seconds smaller than for the explosion that happened 8 minutes earlier. So given that the Earth probably hasn't changed that much in 8 minutes along these ray paths, it suggests that whatever the source of the surface waves are is not necessarily the source of the body waves that we use to produce this event origin time. Interestingly, if you then use the same time shifts, you get a completely different focal mechanism, and the waveform fit is down to 18%. So it's not, you're not produced a good moment tensor in this case. So it's sort of showing the importance of these time shifts and knowing them. And then what we also now try is you going back to the original best fitting time shifts, but changing the filter frequency to much higher frequencies. And now you can see that actually we've produced what looks like a positive isotropic moment tensor. So that's just changing the filter band has completely switched the solution. So these methods are really sensitive to frequency, to time shifts. And what's slightly concerning, I guess, is that if you didn't know the answer you were looking for, you could probably produce quite a range of different solutions. So it's something to think about. And then finally, for the earthquakes, they generally have worse waveform fits, probably because they're noisier and smaller magnitude. But overall, they all produce double couple sources. In terms of characterization, which is what this sort of session's about, we can plot them on the Hudson plot, which is similar or analogous to the loon that some of you may be more familiar with. And the idea being that towards the Y and positive and negative extremities, you're looking towards explosion and implosion, and in the center, you're looking at double couple. And you'll see that the earthquakes in green center around the double couple, the explosions towards the top in more explosion space, and the collapse event is in the bottom right near a negative closing crack. I'll just wrap up with sort of addressing these issues with using surface waves. Here, we've basically taken 2 different depths of sources and plotted the different components of the moment tensor. And you'll see on the left, for a shallow source, 2 components of the moment tensor, MXZ, MYZ, are basically 0 amplitude. They're unconstrained. And so you can imagine that when you're looking at these different sources, when you're near the shallow surface, 2 of your 6 components of your moment tensor are basically unconstrained. So that's why we've got some difficulties. And then finally, if you have a vertical component seismogram for an explosion, which you see at the top, and a vertical component seismogram for a CLVD source, which is what you see at the bottom, you'll see they're basically identical. So if you're a waveform algorithm, it's going to be very difficult to tell the difference between those two source types, and I think that's why we get some of the trade-offs that we see. I'll leave those there because I realise that the time is flashing at me. And yeah, any questions, please?
Thank you, Christopher. Yeah, we are slightly over time. If there's one short question from someone, or we defer the discussion to later. I think we can move on to the next talk then. Thank you.
It's already we still have 3 minutes. These are.
Oh, I'm sorry.
Yeah.
Oh.
These are,
I see. I'm sorry. You can come back to the podium. It was not clear. I should have looked at the starting time. So the timer actually is set on the 3 minutes for the questions. So we will not let you go yet. No questions from the audience. So one question from my side. So your these methods should be used then with some caution in analyzing these events and trying to discriminate. How do you see, or what do you recommend? How do you recommend they should be used?
Yeah, I think at the moment we're still in the sort of development phase. I haven't got through to working out is there a better way using these exact methods. The part of the project will be to look at different inversion codes. So there's MTUQ, TDMT. There's various different methods out there that I need to sort of analyze, and that would be the long-term goal. The other thing with the time shifts, for example, is that we're thinking or considering the idea of altering the location of the event and keep the time shifts identical for each station on a station-by-station basis, certainly for the earthquakes and for the collapse event, and see if actually it's the hypercenter that's causing some of those issues. Yeah. With regards to the collapse event changing the time shifts and getting a completely different answer, if you like, that one is, I haven't got a great answer or solution yet. I think that is part of our conclusion, is that maybe these aren't necessary. You've got to be careful if you're going to do this, and you should really think hard before you start publishing a final answer. Yep. Kind of.
Okay, thank you very much. I think at this point we can move on to introducing the next speaker. Thank you so much. Let's thank the speaker again.